let's look at orthogonality of eigenfunctions. In the Sturm-Liouville problem, we can write the Sturm-Liouville problem out with its boundary conditions, with the restrictions that P and W both need to be strictly positive on the interval. Then we have an operator H that goes from the space of functions with boundary conditions to itself. The operator H is defined as 1 over W minus 1 over W times Py prime prime plus Qy. Then it's associated to the inner product that is just the integral over the interval AB of FGW. Then we can reformulate the ODE, the Sturm-Liouville problem itself, as a standard eigenvalue problem, Hy equals lambda y. And the theorem we're going to build is that the eigenfunctions of H, where H we have proven is self-adjoint, are orthogonal. That is, if you take any two eigenfunctions that are not associated with the same eigenvalue, then their inner product is equal to 0. Let's have a proof. It follows straightforwardly in the same format as the proof for the symmetric matrices. So we have that, I changed from NM and IJ. If we apply the self-adjoint operator to one of the eigenfunctions, we have the associated eigenvalue times the same eigenfunction. We do it twice. We have required that the two eigenvalues are different. Then also the two eigenfunctions are different. Then we take either of the two and make an inner product with the other eigenvalue, with the other eigenfunction. We notice that the first two elements are the same, while the second two are different. So if we take a difference between the two equations, then the first column disappears, while the second column, the lambda I, we retrieve lambda I minus lambda j times the inner product of fi and fj. So the eigenfunction associated with lambda I and the eigenfunction associated with lambda j. But we have said that lambda I and lambda j are different, so the first term cannot be equal to 0, so the second term must be equal to 0. Let's go into the spectral theorem. So the previous statement was a recap of last week. Now we want to build the same spectrum theorem as for symmetric matrices. For symmetric matrices, we have that if we had normalized eigenvectors, then we could write the symmetric matrix as a finite sum over all the eigenvalues times the tensor product of all eigenfunctions by themselves. So VI, tensor product VI. So this was a sort of a restructuring of our symmetric matrix. The same thing we can do for self-adjoint operators. So if H is self-adjoint, and we have normalized the eigenfunctions associated with eigenvectors, then we can write H as an infinite sum of lambda I times phi tensor product phi. Now we haven't introduced a tensor product in case of operators or tensor product between two functions. So eigenfunctions are functions. So the tensor product between two functions A and B is only defined as an operator. So A tensor product B, where A and B are functions, is an operator itself. And operators are usually defined by how they act on other things. So we define the operator A tensor B applied to the function y as A multiplied by the inner product of B and y. Notice that the order in which we are multiplying things matters. For tensor product, it mattered also in finite dimensions. So with vectors x and y, x tensor product y was different than y tensor product x. And here for functions we have the same. A tensor product b is different than b tensor product a. But it's built as just a standard multiplication between the first element and the inner product of the second element times the function that we are applying the operator to. So can we prove the spectral theorem for self-adjoint operators? Well, we're just going to look at an interpretation of it. So we have H applied to Y, and we say that H can be rewritten as this infinite sum, and we can rewrite it by applying the definition of tensor product that we have just seen as an infinite sum of the eigenvalue times the eigenvectors times the inner product between y and phi and the eigenfunctions that we have at the moment. So we can interpret this as we take y, that is the function we want to apply the operator to, we project it on the space, on the direction of one of the eigenfunctions, and that projection we use to rescale by the associated eigenvalue, and then we multiply by the basis. So it's kind of breaking down into in which directions, so to say, they're now functions, but we use them in the same intuition as we did before. In which directions do we stretch most, and in which direction do they contract most? Also, we can use this in the same way as we did for symmetric matrices to rewrite, well, for symmetric matrices, we rewrote any vector x as a finite sum of xi times the eigenvectors vi, where we can find that xi is indeed the projection of x in the direction vi, so x inner product vi. The same formulation can be used for y being a function. Then we can write it as an infinite sum of yi times the eigenfunctions vi, where yi is indeed the inner product between y and phi. So if you look at it this way, we can really think of phi 1, 2, 3, 4, and infinity as an orthonormal basis for the space of functions, where the space of functions is defined as all the functions on the interval AB. We know nothing outside the interval, so we have to stick to that. That are continuous, bounded, and are respecting the boundary conditions. So if we take y inner product phi I, we can rewrite y as this infinite sum. Then for linearity of the inner product, we can take the infinite sum out of the inner product. So now we have an infinite sum of yi times phi I times phi j inner product. But we know that the eigenfunctions are an orthonormal basis, so that product is 1 if I and j are equal, and 0 otherwise. So 0 otherwise means that our infinite sum just collapses to just one value, and the fact that the product is 1 just disappears. So you see that there is a sort of circularity in here. We just proved that we can indeed do that. So when we're applying our self-adjoint operator h to y, this simplifies our mechanism to being an infinite sum of lambda I, phi I, yi. Remember that in this context, lambda I is a real value, phi I is a function, while yi is also a real value, is the inner product between phi I and y. Let's look a little bit at scaling and at boundary conditions. So last week we introduced this problem that we have gone back to multiple times, minus y second equals lambda y in between 0 and L with 0 boundary conditions on the two sides. We can find the eigenvalues, we can find the associated eigenfunctions, we can rescale the eigenfunctions for them to be normalized, and we can find this coefficient k that is 1 over the eigenfunction times itself in the inner product at the power 1/2, so square root of all that. And as we did at the beginning of this week, we can write it as square root of 2 over L. Any f satisfying the boundary conditions can be written as an infinite sum for n going from 1 to infinity of Cn times Pn. That is an infinite sum of Cn times square root of 2 over L times sine of square root lambda times x. So this is the application of what we have seen in just before on this sine expansion, where Cn can be defined as an inner product of f times phi n. If we didn't normalize phi n before, then we would have to define Cn as not only the inner product of f times phi n, but that divided phi n times phi n inner product. We would retrieve the same value. Well, in the second case, Cn would also include the square root of 2 over L. What happens if a function f does not satisfy the boundary conditions? Well, formally, we can still write it as an infinite sum of f inner product phi n times phi n. Does this function still, does this rewriting still make sense? It does. Actually, we still have that the difference between the two computed as an integral is equal to 0. But, well, f does not satisfy the boundary conditions, but f hat kind of needs to satisfy the boundary conditions. What it means is that f and f hat, where f hat is the rewriting of f as a sum of an orthonormal basis that does not satisfy, where the orthonormal base satisfies some boundary conditions, but f doesn't. Well, these two rewriting are the same everywhere except at the boundary.